got everything set up. What do you say we give this a try?
You're ready, I'm ready. You're all right, Claire. Let's do this. Welcome. Over there is Claire, and she's going to handle the technical aspects of this video for us. I'm Rag, and I'll be the narrator. What am I going to narrate? Between this video and the next one, I will show you two of the most fascinating solutions to two of the oldest problems known to us. The first video illustrates a solution for prime numbers. Not only will I show you that we can locate all the prime numbers in the universe, but that we can do it without using no numbers. I mean, how cool is that? The second video will go in depth and explore what growth is and how, through the gravity interlock, all the things we see actually grow. And we will understand why the apple that hit Newton on the head and helped him discover gravity was on the tree in the first place. Yes, I know, it grew there. But what does grow actually mean? With all that being said, let's do this. I should start with a brief explanation of what prime numbers are. The definition of prime numbers are any number that can only be divided by the number 1 and the number itself. The number 3 is a common example of a prime number because it can only be divided by the number 1 and the number itself, the 3. Claire has displayed a typical number line, one we all become familiar with. What would happen is you would start with the number 2 and then cancel out every number that was divisible by 2. The 4, then 6, and so on. Then do the same with the 3, which would then be the 6, then 9, and so on. Then just do the same with every number that is left. As you go down the line, every number you come to is a prime number. Then you mark out their multiple. In the past, this was a long and laborious process. Even today, computers can become overwhelmed finding primes this way. But this way of finding primes is old school. Let's do it a different way. Woo-wee! Look at all the numbers. And here I told you we wouldn't need the numbers to find prime numbers. But don't worry, in a few minutes those numbers will all be gone. Claire just put them up so I can show you why we won't need them. Because we're going to delve into the world of symmetries. What are symmetries? Simply put, things that are different but have similar parts. Like your eyeballs, you have 2 of them, they are different but are similar to each other. Same with your arms, same but different, a left and a right, your legs, ears, and so on. All different but similar. Symmetrical. Now, let's look at the grid of numbers Claire put up. There are 3 things I would like you to notice about what we're looking at. The first thing is, there are 2 symmetrical lines I'd like to show you. One I call the 5 line, and one I call the 7 line. Remember, we are looking for prime numbers. Let's start with the 5 line. If we start on the number 5 and add 6 to it, we go up diagonally to the 11. If we add 6 to the 11, then we go up to the 17. In fact, if we just keep adding 6 to each number, we can go as far down the line as we want. This is the 5 line. Now let's look at the number 7. This will be the start of the 7 line. Again, if we add 6 to the number 7, we go up diagonally to the 13. Keep adding 6 to each number, and we go down the line as far as we want. This is the 7 line. Now if you look at what we've done, you'll see that not counting the numbers 1, 2, and 3, which are prime numbers, the 5 line and the 7 line contain all the prime numbers there are. No matter how hard you look, you will not find any prime numbers that are not on these 2 lines. No matter how far down the grid you go, we can say these 2 lines are symmetrical, different but same. Pretty neat, huh? That means that we could get rid of all the other numbers right now. But we're not ready to do that just yet. Which brings me to the next thing I want to show you, what I call the 7 symmetries. Before we move on, Claire just reminded me to say that we are aware that not every number on the 5 line and the 7 line is a prime number. Numbers like the 25, 35, and 49 are fake primes, sometimes called pseudo-primes or prime wannabes. It is exactly because of these pseudo-primes that no mathematical equation can be written for prime numbers. This all becomes clearer in the third thing we discuss. Okay, the second thing I'm going to show you are the 7 symmetries. These symmetrical patterns are each related to a specific row on the grid. Claire will demonstrate what a row is. Seven rows. Now we can't start with the number 1 because its symmetrical pattern is every number. We start with the number 2. The 2 starts on the second row. If we identify each multiple of the 2 by adding 2, we get the 4, the 6, then the 8, 10, 12, and the 14. When we get back to the 16, we are back on the second row. From now on, every 8th position of the number, the pattern will repeat. This pattern will repeat all the way down the grid. Of course, the number 2 is easy, but this symmetrical pattern works on every number in the row. The next number on the row is the number 9. By adding 9 to 9, you get 18. Then plus 9, you get 27. Do this 7 times and the pattern repeats. Each row has its own distinct symmetrical pattern, and that pattern works on any number in that row. Row 3 has its own unique symmetrical pattern, and every 8th multiple of the number on that row, the pattern will repeat. The 10, the 17. Claire will run some of the patterns for you. So, 7 rows, 7 symmetrical patterns, the 7 symmetries. Phew! Where are we? Keep in mind that I am going to show you how we locate every prime number without using numbers. So far, I have shown you 2 lines that contain all the prime numbers, the 5 line and the 7 line. Then I showed you that every row has a unique symmetrical pattern specific to that row. Now for the third thing I'm going to show you, and this is really cool. Alright, the third thing I want to show you is really cool. I know that most of you have been chomping at the bit, wondering where all those fake prime numbers come from. You ask, if all them numbers on the 5 line and the 7 line are prime numbers, what's going on with all the wannabes? Axiom. Yes, axioms. What's an axiom? The definition I use here is a statement that is taken to be self-evidently true. You will see that they are evidently true statements. So what's the first axiom? Because there are 3 that we come to. The first one, every number on the 5 line times any number on the 7 line, the result will be on the 5 line. Yeah, I know, all those fake primes are being put there by the axioms themselves. If I multiply the 5 times the 7, the result will be the 35 on the 5 line. Let's try the 17 times the 13. The answer is 221, which is on the 5 line. This is an axiom. It is a true statement all the way down the line. Now check this one. Every number on the 5 line times itself or any other number on the 5 line, the result will be on the 7 line. Yes, 5 times 5 equals 25 on the 7 line. 11 times 17 equals 187, also on the 7 line. And here's another axiom, though this one is basically the same as the last one. Every number on the 7 line times itself or any other number on the 7 line, yes, you guessed it, the result will be on the 7 line. 13 times 13 equals 169, 7 line. 7 times 25, yes, the 175 is on the 7 line. I think axioms are so cool, because with them as a foundation, we can exploit the number line. So there you have them, the 3 things I wanted you to know so we can go after all the prime numbers. The 5 line and the 7 line, the 7 symmetries, and the 3 axioms. Now, there's just one more thing to do, and this is just an adjustment to the grid for our own benefit. After that, we'll start the process for finding prime numbers. Up until now, I have been saying "and so on" when referring to the length of the grid, implying that we could extend the 5 line and the 7 line and the symmetrical patterns as far as we want. Now this is true. They can go into infinity. But that's not realistic for us. And trying to manipulate an unending grid is not a sustainable endeavor. We must contain the grid into a manageable form. And this is arbitrary, meaning we can make the container to be any length we want. For some reason, though, there seems to be a certain length that works the best. The grid container appears to work the best when it is based on the number 1260, 1260. When the grid is set at 1260, everything seems to fit in place. Keeping track of the columns of the grid up till now wasn't necessary. If I want to contain it, though, I will need to number the columns. I already know that I will contain the grid at 1260, so I will want to make the grid columns accommodate this. To do this, we know there are 7 rows. The 7th row will always have a multiple of the number 7. The numbers of the column then will represent what a multiple of 7 will be. Column numbers 1, 2, 3, 4, and so on will represent the value of 7 in the column. First column, 1 times 7. Second column, 2 times 7, 14. 3 times 7, 21. 4 times 7, 28, and on down the grid. Now we want to get to the grid number 1260. When 1260 is divided by 7, we get 180. So the grid should be 180 columns long. This is a 180 column grid. This is where the small home computer systems really start screaming. But if we look at this grid, we notice something truly beneficial. If we count all the yellow squares on the 5 line, we get 210 squares. And if we count all the red squares on the 7 line, we get 210 squares. We can now make two grids, one of the 5 line, 210 squares, and one grid of the 7 line, 210 squares. And each of these grids are only 30 columns long, and they contain all the prime numbers and the fake ones that we condensed down from the 1260 grid. When the grid was contained to only hold 1260 numbers, all aligned in columns of 7s, we ended up also containing the 5 line and the 7 line. Each one of these lines are now grids themselves, and we no longer need to concern ourselves with the rest of the numbers on the original grid. Now let's bring back the 3 things I showed you in the beginning. Can you remember any of them? The first one was the 5 line and the 7 line. But they are no longer lines. They are grids now. So we can forget that thing. The second thing was the 7 symmetries. Well, we have 2 grids. Each one still has 7 rows, so the symmetries must still exist. And they do. They are in a different order than before, and the expansion between them is 42 instead of the original 7, but everything is still intact. And the third thing was, you guessed it, the axioms. First axiom we learned, every number on the 5 line times any number on the 7 line, the result will be on the 5 line. So what that means now is, any yellow one times any red one, the answer is on the yellow. The second axiom we learned, every number on the 5 line times itself, or any other number on the 5 line, the result will be on the 7 line. So, yellow times yellow, answer on red. That's pretty basic. The third axiom, every number on the 7 line times itself, or any other number on the 7 line, the result will be on the 7 line. Again, red times red equals red. Wow! Everything we did only to end up with 2 smaller grids, a yellow one and a red one. 7 rearranged symmetries, but they're still intact. And yellow times red equals yellow, yellow times yellow equals red, and red times red equals red. Man, getting down to the bare bones like that, you might ask, why not just get rid of the numbers too? Okay. That's it. Enough. This has to end. So there is more I could show and tell you. More about the symmetrical patterns, more about the expansion between the numbers, more about the number line. There just is more. But it's time to put what we know together. We know we have 2 grids. We know how the symmetrical patterns work, and we have the axiom. What I'm going to do now is focus on one axiom, the first one. Yellow times red equals yellow. I'll only present this axiom, but you'll be able to see how the other axioms apply. I'm going to change the way the axiom reads from yellow times red to red times yellow. Same thing, this is just for display purposes. Alright, red times yellow on yellow. Let's see, the 1 times the 5 on the yellow, the 7 times the 5 on the yellow, 13 times the 5 on the yellow, 19 times the 5 on the yellow. Hey, look at the pattern developing on the yellow. It looks just like one of the 7 symmetries, the one on the first row. I'll bet the next position of the pattern will be on the 125. Yes, it is. 25 times the 5 on the yellow. I bet the red numbers 31 and 37, both times 5, are the next 2 positions of the symmetrical pattern. and then it will repeat. Let's see. Yep, and repeat with the 43. Let's try the number 11 then. Okay, 1 times 11 on the yellow, 7 times the 11 on the yellow, 13 times 11. Looks like the second symmetrical pattern is developing. What's that mean? Since the first axiom holds true, and the 7 symmetrical patterns are true, then that means, wow, we don't need the red grid. Then we don't need the multiplied yellow grid. Hello, we don't even need the numbers. We have a yellow grid and 7 symmetrical patterns. That's all we need. Right before these numbers disappear, I want to show you something about the expansion. This is a small example, but it will give you a gist of the expansion we get into next. As you may have figured out by now, this whole grid process is symmetrical. Look at the first column, the numbers 5 through 41. Now the second column, the 47 to 83. They are just the first column plus 42. 5 plus 42 equals 47. The 11 plus 42 equals 53, and so on. Since the expansion is 42, then every column is plus 42. So then if we moved the column numbers down one space and add a 0 to the beginning, every column number would then indicate the underlying numbers of 42. Now every column is just 5 through 41, but with an expansion amount of 42 times the column number. That means that in the new column, number 1, the number 83 is just the number 41, with an underlying expansion of 42. The next column is a 41 with an underlying expansion of 2 times 42, because the column number is 2. Do you see the expansion of 42? Just an example of horizontal expansion. I just showed you this to help you understand the concept of expansion. We are not going to use horizontal expansion. We are going to use vertical expansion. The difference is that instead of going horizontally down the number line, we contained the line into grids of 1260. So now we go vertically up. The underlying vertical expansion is 1260, and the first grid starts with 0 also. When we look at the vertical expansion in our current grid form, we can tell that we're not going to get very far before we run out of room. Those grids just aren't going to work. What we do then is stretch the grid into a single or linear line. In doing this, we change the columns and rows into positions. We have 210 positions because the grid was 30 columns with 7 rows, so 30 times 7 is 210. We can now display the grids better. The first grid will be 0, just like the 0 we used in the column numbers in the expansion of 42s. These grids are based on 1260. Because the 0 grid starts on 5 and ends on 1259, there is no 1260 value. Just like in the 42 scenario, where the numbers of the columns represent the underlying expansions of 42. Now the grid number represents the underlying expansion of 1260 for the grids. Grid 0 starts on the 5. Grid 1 starts on the 1265. 1260 plus 5. The grid number will always tell us where we are because the first position on the grid will always be the grid number times 1260 plus 5. Unfortunately, I was hoping to get more than 14 grids displayed so I could show you how the symmetrical patterns change into vertical patterns. They are very simple patterns. The number 5 is in the first position. The symmetrical pattern of the first row shows that the next instance of the pattern will be on the 35, which is in the 6th position. The first position of any symmetrical pattern tells you how many positions to count up. The first position, which is the number 5 in this case, tells you that you should add the 5 to the first position. This takes you to the 35, which is in the 6th position. First position plus 5 to the 6th position. Plus 5 again takes you to the 11th position, the 65. This counting method is fine for the numbers 5 or 11 or any of the smaller numbers. Doing it this way is actually the horizontal expansion. But we are starting with the number 1 grid. We know that the first position of that grid contains the number 1265. The grid number, which is 1, times 1260 plus 5. We don't count up to 1265 positions to find the second instant of the symmetrical pattern. The first 3 numbers, the 7 line, are 1, 7, and 13. Since we start with grid 1, the first number is 1265. So 1 times 1265 leaves it right where it is. To find the second instance, we multiply 7 times the 1265. This equals 8855. When we break the 8855 down, we find 1260 times 7, the grid number. And then multiply 5 times 7. This is the position. This indicates that there are 7 1260s. So we go to the 7th grid, and the 35 is in the 6th position on the grid, which is the second instance of the symmetrical pattern. Now this seems so involved. Look once again. What we see is that we started on grid 1. We add 6 to grid 1 and we get grid 7. Once on grid 7, we went to the second position of the pattern. What that means is that 6 is the underlying expansion for the whole grid. As a matter of fact, this expansion is directly related to the grid numbers. Grid 1 has a basic underlying expansion of 1 times 6. Grid 2 is 2 times 6. 3 is 3 times 6, and so on. So if we just add 6 to the 7, we get 13. If we go to the 13th grid and to the 3rd position of the symmetrical pattern, we will find the number 16,445. This breaks down into 13 times 1260 for the grids, plus the 65 for the 3rd position. This seems hard to explain, but it is a very simple process. There are position charts that illustrate this very clearly, but they are too much for this animation. Another thing I can't cover here is the small expansion. The small expansion exists because we contain the lines into grids and the symmetrical patterns hit the end of these grids and must reset back to the first position when this happens. Also a very simple process, and there is a chart for this, which is too much for this animation. All this time, I have been trying to show you what and how this grid system expands. I did this using the 1260 and all of its included multiples. What happens now is to go vertical, to stack grid on grid on grid into the infinite. I can't do that with this animation. A large computer system using this symmetrical system could, within a few seconds, process prime numbers we never heard of. A short time after that, it would produce the last prime number. There are 2 scenarios I can see happen. One, the one I think is more feasible, is that the symmetries are cumulative. This means that whatever grid you're on, the first grid and all the grids in between must be processed against it. Eventually, all these accumulated grids will overwhelm the grids at the end, and there will no longer be any primes. Honestly, I don't think this is very far down the number line. The second scenario would be if the symmetrical patterns settle down into an intertwining system. Compare this to an electrical wire that has 7 intertwining strands of wire inside it. If the symmetrical pattern did this, then prime numbers may be infinite. I think it's exciting either way, and we should know. If you've made it this far, I'm going to confess an honesty to you. Everything I just showed you about looking for prime numbers by using the grid symmetries and the symmetrical patterns is totally disrespectful to this universe. This symmetry is one of the foundation parameters of everything we know. It underlies everything we see. I use this symmetry to bastardize a solution for prime numbers. Compare this to a piano. It has 88 keys. If you only pick out notes for a song, you disregard or disrespect every other note. You pulled your song out of the whole, as I did with prime numbers. Finding the answer to prime numbers is admirable, but they are just the tip of the iceberg to this universe and to what my next animation will illustrate. Gravity.